Hello everyone, welcome back in the next video in this series of linear algebra questions that are asked in the GATE examination in the previous year. So let's start this video with this first question. So first question first says, for a matrix we have a matrix which has a dimension of 2 cross 2. One of the normalized eigenvector here. Notice the term normalized, and what is the normalized vector in general way? The normalized vector, it is the vector which has a magnitude of 1. So now if I have any vector and which is normalized, then I can say the magnitude of any vector is 1. Then and then I can say it is a normal vector. So now here the same concept we have to use that we have used in our previous video. Ax equal to lambda x, and here this a is our matrix, x is our vector, and here this lambda is any scalar. And if this condition is going to hold, then we can say here this vector x is nothing but our eigenvector for this particular matrix A. So now the matrix A is given in the question. So let's start from the option A. We have to go through the option one by one. So let's start with the option A. So now let's forget about this factor, because it is just a factor to make it factor is present because to make the vector as normalized. So now let's forget about it. So just simply focus on this vector which has value of 3 minus 1. So now let's do the multiplication. So here 50 minus 3, so I am getting 12 as first entry, and here 3 minus 3, so I am getting 0. So now you can see, let's try to represent this 12 comma 0 matrix as lambda times this 3 comma minus 1. So now we can say we are not getting any scalar here to represent this left hand side vector in this right hand side form. So I can say option A is not correct for this question. So now let's move to the option B. Again, let's put this matrix as it is. Now we have to multiply it with vector which is given in the option B and which is 1 comma 2. So now let's again do the matrix multiplication here. So 5 plus 6 11, and here 3 plus 2, so 5. Again you can see here the same way we are not getting any scalar to represent this vector in this lambda time x. So again we have to put here not equal to. So now let's move to the option C. Same vector here, 5 3 1 3, but here we have to put a vector which is given in the option C and which has value of minus 1 comma 1, sorry 1 comma minus 1. And let's do the multiplication. So 5 minus 3 plus 2, and here 1 minus 3 minus 2. So now you can easily see that if I bring 2 out from this vector, then I end up with this 1 comma minus 1 vector, and which is the initial one. So I can say the vector is repeating here. So now this 1 comma minus 1 is the eigenvector for this matrix A here. But further more step we have to normalize it. So simply we have to divide this vector with its magnitude. So here the magnitude will be root 2. So it is our normalized eigenvector. So option C contain the correct answer, the same as this one. Okay, now let's move to the question number 2. Okay, question 2 has a system of equation in this matrix form. We generally denote as Ax equal to B, and here A is nothing but our coefficient matrix. Our coefficient matrix. And here this x is our variable vector. Here the variable vector is in the form of x1 and x2, and B is again the vector. Now here you may see that value for B here is 0 0. So in the other word, here B is a 0 vector. B is 0 vector. So now it is the system of equation which are homogeneous. So I can say this system is homogeneous. So now for the homogeneous system, we are always going to get a solution because the right hand side of this equation is 0, and if I select the all variable here is 0, then I must satisfy this equation because the left hand side is also 0 and right hand side is already 0. So this equation will satisfy for 0 0 as the value of this variable, and we are calling it as a trivial solution. So now for the homogeneous system, the system is always consistent and the solution is nothing but this origin because the line, basically this equation represent a line. For the homogeneous system, the all the line must be passed through the origin because they have not any constant term in this equation, so they all must have to pass from this origin. For this homogeneous system of equation, it it does not matter how many equation we have. If the all equation are homogeneous, then they must have to pass from this origin. So this point is nothing but represented by 0 0, and it is the our solution for all homogeneous system, and we are calling it as a trivial solution. So now here we are at least getting the solution. But now look at the option B. Option B says no solution. So option B automatically cancel out because the system is homogeneous. Then we are always going to get the solution. So now the next step is that to find this correct answer from these three statements, what we have to do, we have to first of all reduce this coefficient matrix. Let's first of all form the augmented matrix. Augmented matrix. So here our coefficient matrix has value of 2 minus 2, 1 minus 1, and let's bring this right hand side here. So now to find the rank, we have to reduce this matrix into echelon form. To do this, we have to perform some row operation. So here you may notice this first row is twice as large as this second one. So let's make this first one as 0. So I can write like this: r1 minus 2 times r2 will make my new r1. So now after this, what we are getting, let's write it here. So this first row will all entries become 0, and this second one remain as it is. So now here one may say that here the only one column, one linearly independent row I am getting. So I can say here the rank of the coefficient matrix is 1, and also the rank of augmented matrix with including this column, it does not make any difference because the right hand side here is 0 0 vector. So again it is exactly same as rank of coefficient matrix. Here the rank of augmented matrix is also the unity. So now from the basic concept of the solution of simultaneous linear equation, we can say if this condition is going to hold, then system is consistent, and it is the always going to hold for the homogeneous system because system is always consistent. So now but we are not sure that after either we are getting a trivial solution or infinite solution. So now to reach the final conclusion, let's compare this rank with the number of unknown. So here the rank is 2 and the number of unknown we have are 2 in this term of x1 and x2. So I can say here this matrix, in the other word, this system has a rank deficient, and it's deficient by the rank 1. So I can say here at least one variable is independent. So we have two variable x1 and x2. So I can say here x2 is, it can take any value t, and here t belongs to any real number r. So now in the same way I can also write then x1 is also equal to t, because if you form the linear equation from this second row, then what we are getting is just x2 minus x1 equal to 0. So one can say x1 is exactly same as x2. So now it is the equation that we are getting from this reduced matrix. So now we have to select any general variable for either x1 or x2. It does not make any it isn't make any difference if either you are selecting this x1 as free variable or x2, because they are both equal. So now the system has multiple solution from this. Here the t may take any value like 1, 2, 3, 5, 6 and anything it may take. Then the system is always going to satisfy with the this number. So now option D is the correct answer for this question. Okay, now let's solve question 3. Here in the question 3, sorry, I have make mistake here. Here the eigenvalue has value eigenvector as 1 comma minus 1, not plus 1. So here minus 1. So now here a matrix has eigenvalue -1 and -2. The corresponding eigenvectors are 1 comma minus 1 and 1 comma minus 2 respectively, and the matrix is okay. So here in this question we have to go in the reverse direction, because in the general question we have given the matrix and they are asking about the either eigenvector or eigenvalue, but here the condition is totally reverse. We have given the eigenvalue and eigenvector and they are asking about the matrix. So now the procedure is still same. What we have to do is just simply use some property and go through these four options. Now the first property is that the sum of two eigenvalue here, lambda 1 and lambda 2, it is nothing but the trace of matrix, and the multiplication of this two eigenvalue, it is the it will give me a determinant of matrix here. So now let's start with the option A. So now here the trace for this matrix, it must be -3, because the sum of these two -1 and -2 will be -3. So here the sum is -3. So in other words I can say I have to select the matrix from these four matrices which has a trace of -3, -3. So let's try to find the trace from for this four matrix. Now here the trace is nothing but the sum of the diagonal element. Here the sum of these two will be -1. So I can say option A is automatically cancel out. Option B has trace of -3. Just sum these two number. So yes, option B may be the correct one. Option C has also trace of -3. So also yes, option C is also possibility, and option D also has a trace of -3. Just add these two number. So again, option D is also maybe correct one. So now the second step is that we have to find the determinant, and here the from this property we can say the determinant of the matrix, it must be +2. So now from these three matrices we have to select the matrices we have determinant of which have a determinant of 2. So now let's find the determinant of this B matrix. Here I am getting -4 and +4, so determinant is 0 for this option B. So again option B is not the correct matrix for this according to sorry with respect to this property, sorry this eigenvalue and this eigenvector. So now option C has a determinant of +2. Yes, option C is still there, and option D also have the determinant of +2. So yes, we have still two options. So we have done our work 50% and still we have to do the 50% work. So now let's move to the next concept, and which is concept of eigenvector, this one. So now here matrix is given in this options C and D. So let's first of all check for the option C. So option C has a matrix in this form -1, 0, 1 and -2. So let's multiply it with one of its eigenvector. Let's select this one, 1 -1. Remember here we have -1. So now let's do the multiplication. So here we are getting +1 and 2. So now you can easily see that we are not going to get any scalar to represent this vector in this lambda time the initial one. So I can say this condition is not going to hold for any scalar here lambda. So I can say the option C is not correct one, because it is not satisfying this condition for this eigenvector. In the other word I can say this 1 comma -1 vector, it it is not the eigenvector for this matrix. So option C is also cancelled out. The only remaining option is D, and which is of course correct. Let's check it for your clarity. So here we have matrix in this form, and here let's put again this vector 1 comma minus 1, and let's do the multiplication. So here I am getting minus 1 and here I am getting plus 1. So now if I take the minus 1 common from this matrix, sorry, this vector, to represent this vector in this lambda time initial one, and initial one is this one, so I can write like this. So now you can see I have represented this matrix in this lambda time initial one, and here this scalar is nothing but our eigenvalue, and which is here in this case minus 1. So now you can check in the reverse direction also. The one of the eigenvalue is minus 1. Yes, it is the correct one. So now in the same way you can also check for this vector, and you are getting lambda is minus 2, and again it is the second eigenvalue. So now we can say option D is the correct matrix which has this set of eigenvalue and this set of eigenvector. So now with the help of this 2 to 3 property, we can say we can easily find the matrix with the help of this eigenvalue and eigenvector. So now let's move to the question 4. Okay, now let's solve this question 4. So question 4 asking about the one of the eigenvector of this matrix. Here the matrix we have 4 cross 4. So now again we have to use the same concept that we have used in this series dozen of time, which is ax equal to lambda x. So it is the basic definition of eigenvector. So now again we have the matrix A here. Let's call it matrix A here. So now again we have to go through these four options one by one, and we have to check which one of the option is satisfying this condition. So now let's put the matrix here first. So now here first of all let's start with the option A. So option A has a vector like this 1 minus 1 2 and 1. So now let's do the matrix multiplication to find the resultant vector. So now here the first entry will also 5. Here this entry is 5. Now the second one will be minus 5, and the third one 4 plus 1 again plus 5, and the last one is 6 plus 1, so 7. So now if I want to represent this vector in this lambda times the initial one, here the lambda will be any real number, the initial vector, which is look like this. So now we can easily see that we are not going to get any lambda here to represent this vector in this form. So let's put not equal to here, because this condition is not going to hold for any real value of lambda. So now option A does not contain the correct eigenvector for this matrix. So now let's move to the next option, which is option B. So again let's write this matrix as it is. So now let's multiply it with vector which is given in the option B. Let's find the resultant vector after the multiplication. So here the first entry will be 0, second will also 0, third entry will be 2, and the last one is 3. So now again let's represent this in this lambda times the initial one, and the initial vector is this one 2 2 1 0. So now again I can say we are not going to get any scalar here to represent this vector in this form. So again let's put not equal to here also. So now let's move to the next question, sorry, next option, and which is option C. So let's put the matrix as it is here 5 0 0 0 0 5. So now let's multiply it with vector which is present in the option C. So let's find the resultant vector. So now here the first entry will be plus 5, second entry will be minus 10, third entry will be 0, and fourth one is also 0. So now the same procedure. Let's try to find out some scalar here to represent this 5 minus 10 0 0 vector in this lambda time this initial one 1 minus 2 0 0. So let's write it here 1 minus 2 0 0. So one can say if I select this lambda equal to 5, then if I multiply this number with 5, then here left hand and right hand side will equal, and here this 2 with plus 5, so again minus 10, here 0 also 0, then all is good for the value of lambda equal to 5. So I can say here this is the one of the eigenvector corresponding to the eigenvalue of 5 and corresponding to this matrix. So now option C contains the correct one of the eigenvector for this matrix. So now option C is the correct one for this question. Now let's move to the question number 5. Okay, let's solve question number 5. So question 5, in question 5 we have three equation and three unknown x, y and z. So they are asking about the solution of this system of equation. So first of all we can represent this equation in this matrix notation like ax equal to b. Here a is our coefficient matrix, b is our variable vectors. Here sorry, x is our variable vector. Here the variable are x, y and z, and this b is again the vector formed with this right hand side of this equation. So now from this matrix we have to form the augmented matrix. Augmented matrix. Augmented matrix. So now let's directly form the augmented matrix. So I have to put the coefficient matrix here 1 minus 2 1 2 1 1 1 minus 1 and 1, and let's put the vertical line here to distinguish it with the right hand side 5 and 1. So I have formed the augmented matrix. So now to find the solution we have to reduce this matrix into echelon form. For that we have to perform some row operation. So now I have to make this entry and this entry as 0. So now what I am going to do is just simply let's subtract 2 times first row from this second row, and it will give me a new R2, and let's subtract this first one with this row 3. So I can say R3 minus R1, and it will make new R3. So now after this two operation what I am getting, let's write it here. The first row will remain as it is 1 2 1 4. The second row will be here by getting 0, here minus 4 plus 1 so minus 3, and here minus 2 plus 1 so minus 1, here minus 8 plus 5 so minus 3. Now in the third row here again we are getting 0, here let's multiply it with minus 1 so minus 2 minus 1 minus 3, here minus 1 and plus 1 again will make 0, and here minus 4 and plus 1 so minus 3. So now here we have to still apply one more operation to reduce this matrix into echelon form. So let's further reduce this entry as 0. So I can say if I subtract this second row from this third row, then this entry will be 0. So I can say R2 R3 minus R2, and it will make new R3. So now after that what we are getting, let put it here 1 2 1, here 4. The second row will also remain as it is because we are doing the things with third row. Now the third row will be 0 0. Here we have to multiply this with minus 1 so it will be plus 1, so plus 1, and here again minus 3 and 0, so again sorry minus 3 and plus 3 will make 0. So now you can see the system is consistent and it has unique solution because the rank of coefficient matrix and augmented matrix are exactly identical, and which is 3, and which is exactly same as the number of unknown. Here the number of unknown is 3 in terms of x, y and z. So now we have to find the value also. So now let's back substitute from here. So we can say I think there is some mistake in this question, so let's check it here. Yes, I am missing here the factor of 2 here. I have factor of 2 in the front of this z in the second equation. So let's make this factor as 2. Sorry for that here for this typing mistake. So now here again let's so this entry will also change because we have changed this entry. So now here I am getting minus 2. So here this entry will also 0 because there is already plus 2. So now here also 0 I am getting. So now here also what I am getting is, so here this entry will also change because we have 0. So again we are here also we are getting 0 after this row operation. So now I can say this matrix has a rank of 2, not 3 here. So this matrix has a rank as 2 and which is less than the number of unknown. Here the number of unknown is 3. So I can say the system is a rank deficient here. Then here from this third row I can say this z variable here, it is independent and it can take any value. Let's call it t, and t belongs to any real number. So now I can say the system has infinitely many solutions because the system is rank deficient and at least one variable is independent. So now the option D is the correct condition for this three equation linear equation. So now let's move to the question 6. Okay, now let's solve question 6. So question 6 says consider the following two statements. So that first statement says the maximum number of linearly independent column vector of matrix A is called the rank of A. Yes, it is the basic definition of rank. The rank of the particular matrix is nothing but the maximum number of linearly independent rows or column. Both are equal. Either we are counting for column or row, we are still getting the same row, same rank. So yes, statement first is correct, of course. So now let's move to the second statement. Statement 2 says if A is n cross n square matrix, then it will be a non-singular if the rank of A is n. Here, first of all, recall this definition of non-singular. Even I have defined this concept in the previous video. If the I am getting determinant as non-zero, then I call it the as a non-singular matrix because here the word is non is in front of singular. So if I am getting the determinant as non equal to 0, then the matrix will be non-singular. But now when I am getting the determinant as non equal to 0, if the matrix has a full rank, in the other word, the my matrix has all the three rows or three column. In the case of 3 cross 3, if these three rows or three columns are linearly independent, then I am getting the determinant as non equal to 0 for this any 3 cross 3. In the other word, I can say if the matrix has a rank of 3, or in the other word, the rank full rank matrix, these all are the equivalent statement, then the determinant it must be not equal to 0 and the matrix will be a non-singular. So here it is given in the statement if A is n cross n square matrix, then it will be non-singular if the rank of A is n. That means A has full rank. So yes, it is the non-singular because all the n rows and n columns of particular this square particular of for this n cross n square matrix are linearly independent. So yes, I am getting the determinant as not non-equal to 0. So both statement are true. So option A is the correct choice for this question. So now let's solve question 7. So question 7 says if A, B, C are a square matrices of the same order. Yes, here this is the important because the order is same for these three matrices. Then they're asking about the inverse of this multiplication. So now here we know if I want to find the inverse of this multiplication, then just what I have to do, I have to multiply individual inverse, but in the reverse order. I have to multiply B inverse with A inverse to find the inverse of this AB matrix. But now here we have three matrices ABC. So first of all, let's make a group of two matrices from this. So let's I can form the group for this BC matrices like this, and the inverse is as it is. So now with the help of this concept, we can represent this BC as in one unit. So we can write this equal to BC whole inverse multiplied with A inverse. Now again apply the concept of this individual, so to applying the inverse to individual matrix for this BC. So again I have to flip this B and C, so I can write like C inverse multiplied with B inverse multiplied with A inverse. So now it is exactly same as this left hand side. So now that is what they are asking in this question. So here option A is the correct in the correct order, because C inverse B inverse A inverse C inverse B inverse A inverse. So option A is the equivalent to this condition. So now let's move to the question 8. So now here again in the question 8 we have a 3 equation and 3 unknown x1 x2 and x3. Again they are asking about the condition for the solution. So again we can represent this system of equation in this matrix form, and from this we can form the augmented matrix like this. So let's directly form the augmented matrix. So here the coefficient matrix is 1 2 3 0 1 1 0 2 2. Here the this equation are non-homogeneous because the left hand side is non-zero, sorry right hand side is non-zero. So now we have formed the augmented matrix. Now to find the solution, so to find the condition of solution we have to reduce this matrix into echelon form. So we just want to make this entry as 0, this one, because there is already two zeros are present. So the only this 2 will be, if this 2 will be reduced to 0, then our matrix in the matrix reduced into echelon form. So let's perform here operation like this: row 3 minus 2 times row 2, and it will give me a new row 3. So now if I am doing this step, then what my matrix will look like after this. So let's write it here. So now here the this entry will be 0, this also 0, and this will be plus 2. So now here one may can say the rank of coefficient matrix here, it is the 2, the number of linearly independent column, sorry rows or column. Here the number of rows are 2 which are non-zero. So I can say the rank of coefficient matrix here is 2, and the rank of augmented matrix is 3, because in the augmented matrix we have to include this last column, and here the entry is non-zero, so we also have to consider this third row. So the number of non-zero rows or independent rows are 3 for the augmented matrix. So now the rank of coefficient matrix and augmented matrix are not identical, so we can say the system is inconsistent. One may directly say from this two equation, because if you see carefully uh, this third row is twice as much as this second row, but here on the right hand side we still are getting, we have 0. If here we are getting a minus 2, then we can say the system has infinite solution, because here the right hand side is 0 for this third row. So we can say the system is inconsistent because these two lines are never going to intersect. So now the system has a no solution, so option A is the correct one. If you draw this three line in the 3 dimension, it is basically a represent a plane. So these three plane are not going to intersect at one particular point. So in the other word, these three plane have not a common intersection point, so the system has a no solution. Okay, now let's solve question 9. Question 9 says the dimension of null space of the matrix. Null space, something looks like difference, but now here the null space is nothing but the nullity of any particular matrix, and nullity is the measure of how much the matrix is rank deficient. In the other word, I have to just what we have to do is we have to find the rank of this matrix and subtract it from its dimension. Here the dimension is 3 cross 3, so at most point most it has a rank of 3. It cannot have a rank greater than 3, because remember rank is must be less than or equal to minimum of either number of rows or column. Here the number of rows and column are 3, so rank of this matrix is less than or equal to 3. So this matrix has at most has a rank of 3, But now they are asking about the null space. So we have to find the rank of this matrix by reducing it to echelon form, and we have to subtract rank from this maximum 3, and so we are end up with the null space. So now let's first of all put the matrix here, and now to reduce it into echelon form we have to perform some row operation. So now here I want to make this entry as 0. So now let's subtract, sorry, add this row 2 in this row 3, and it will give new row 3. So if I'm doing these things, so after this what my matrix look like this second row also remain as it is. Here I am getting 0, -1 and -1. So now further I have to reduce this entry as 0. So now you can see this row is nothing but the negative of this first row. So I can simply correlate and say that this third row is linearly dependent on the first row. So further let further reduce this third row also. So I can write like this: r3 plus r1, and it will make new r3. So now after that my matrix look like this. This first row again remain as it is, second also remain as it is, 1 -1 0, and this third one will be 0 as 0 0, because they are going to cancel with this plus 1 from this one. So now one can say the linearly independent rows or column in this particular matrix is 2. So rank is 2 in this case. You can also reduce this entry 1 as 0 with the help of some further column operation, and we can say the number of linearly independent rows or columns are 1, sorry, 2 in this question. So the rank of this particular matrix is 2, and it is deficient by the one dimension. So I can say the rank is deficient because it has not the full rank which could it have, and which is 3. So I can say it has deficiency of 1. So it is represented by null space. So here the null space is 1 because the rank is 2. So the another I can write the further conclusion like that: rank of any matrix plus null space, or sometimes called nullity, null space, give me the dimension of matrix, or in other words the maximum possible rank. So now the null space here is 1. So option B is the correct one. So now let's solve the last problem for this particular video. Question 10 says one pair of eigenvector corresponding to the two eigenvalues of the matrix. Again we have to use the same concept. This concept Ax equal to lambda x. This concept is repeating in the GATE exam so many times regarding to this eigenvectors. So now again we have to go through the option. So let's write the matrix here. Let's start with the option A. So option A has eigenvector in this form. Here we have eigenvector in this complex form. So now let's do the matrix multiplication here. So I am getting plus I. Let's represent J. In question we have J, and here 1. So here if you try to find out some scalar here to represent this vector in this lambda times the initial one, so one can say if let's here J has value of I, then I can say here after multiplication I am getting here J, and here I am getting minus J square, and it will be plus 1. So yeah, and so yes, here the value of lambda is J. If I select here the value of lambda is J, remember that here the J is eigenvalue, and eigenvalue may be real or complex for any particular matrix. So now the first this vector 1 comma minus J is the correct eigenvector for this matrix. So now the only option A has this vector. So option A must be the correct set of eigenvector. So now let's also check for this second vector, which is j comma minus 1 0 minus 1 1 0. Let's multiply it with vector this j comma minus 1. So now let's do the matrix multiplication. So here I am getting plus 1, in here I am getting j. So now again let's try to find out some scalar here to represent this matrix in this form, j times minus I. So now here the if I want to make this entry as 1 after multiplication of lambda, then I can say here the lambda must be minus j. In the other word, let's simplify here 1 j. We are interested in finding some here value of lambda, so I can multiply this lambda with inside minus lambda. So if you compare these two elements, so one can easily say the value of lambda is minus j here, and if you put minus j here, so minus j square, and it will be plus 1. So we are getting the initial vector, which is 1 comma j. So yes, we have find out the two eigenvector. So also this is the second eigenvector, and we also have find out the eigenvalue, which are j and minus j. You can also check in the counter direction. Let's find the eigenvalue from here. So one can directly make the determinant here and equate this determinant equal to 0. So I can say lambda square plus 1 equal to 0. So further simplifying, lambda square equal to minus 1. So lambda will be j and minus j, and here j is the complex number, j equal to under root of negative 1. So the correct set of vectors for this matrix is given in the option A. So option A is the correct set of eigenvector, and that's it. We have solved our problem in this video, and thanks for watching this video.